Cool. Thank you very much. Cool. I gave this talk last week at our local seminar group, so if you've seen it before, new title slide that looks fancy. The rest of it's the same, so feel free to nod off, especially you, James. That's fine. Cool. Thank you. Cool. Right. So my interest is I like dependently typed programming, but I tend to use it to build more trustworthy software or to look at building highly assured compilers using standard techniques. And one of the things I'm interested in is failure, okay? So to start, and when I mean failure, I mean runtime failure, okay? So I've got a very simple program on here that's in the IO computation context that takes a list of natural numbers, checks to see if they are all 0, and if they are all 0, it will print something out to the user. Because I'm building interactive systems and I want to communicate to the users not just why something is correct, but why something fails. Now, to give you a bit of intuition that we're in a dependently typed language, we're in interest 2 itself, and our all is actually quite powerful. It's a quantifier that says, for any given predicate, does it hold across all items in the list, okay? And the predicate we were using is 0, okay? But the problem is, I'm using nothing on the right-hand side from the left-hand side. Now I'm going to ignore the positive case where we say yes, and look at the no. I have a reason why a list might not contain a 0. Why am I not using it? Okay, to give you some intuition for this. Oh, wrong one. I have an extract from my REPL, okay, where I have called, oh, spoiler alert, how'd you go back? Cool, right. I have called all the 0 on a list that is full of zeros, and it brings me the proof that every element in that list is 0. So far, so good. But I've called it on a list where something isn't 0, and I get a computation, i.e. a proof of void, which is frankly absurd. And I can't use this proof of void at runtime to tell my user why that list that is given is all non-zero. We could guess it, and that's why I've said some non-zero, but I don't want to say some, I want to say precisely what is causing the error. Okay? And the reason why this happens is because we've got this powerful data type called dec, decidable, and we're saying, well, for any given predicate, if it's decidable, we can give you an inhabitant of that type. And if it's not, if you can't find an inhabitant, we'll give you a proof of void. But remember, this is, for me, it's a, compile time only function. I can't use it at runtime. Okay? And that's a problem. And how do we solve it? Well, I'm going to step into the notion of constructive negation. Greg mentioned this on, I think it was Tuesday, highlighting. And the whole idea here is that 2 positive actions can lead to nothing, and that we want to reframe all our negativity about why something fails more positively. And what I don't want to happen is to have a proof of void appear at runtime. I want to have positive information that says why something fails. And the very simple idea here is we can construct a record which has 2 types, one that holds positive information, one that holds negative information. And we can say that at compile time, we have a proof that these 2 things, when placed together, cancel each other out. And to me, that's a very powerful notion of saying, well, instead of having a proof of void, we have 2 things that cancel each other. And what that means is we can actually reframe what decidability is in more simpler terms that we know and love, which is the either. Where if we have an, right, not my thing, so it's right. So what we can reframe it as saying, well, if we have a decidable thing, we can take the projection for the left case, say, here is proof that it was negative, and if it's positive, we've got the right case. Okay, is that okay with everyone? Cool. And I'm not the first one to look at this, as you saw this snippet. So I have a colleague, Bob, and in 2022, he had a talk at the Mathematical Structural Programming on data type negation. He takes a very principled approach to looking at this. I think of myself more as a proof engineer, and I just hack away. And this is what I want to talk about, is what my experience of doing this framework. But also, this is the middle of my journey. And the last bit of the talk is where I want to talk about where I started from and how we can actually take some of this stuff and try and maybe backport it to what we have, maybe in a less more principled fashion, but in a more useful one. So to give you an example, I have is 0. Okay, this is what we had in the very first slide where we say, I am pairing two data types, is 0 and non-zero. And I'm saying is 0 is my positive thing, non-zero is my negative thing, and we have a proof that they two cancel. This is very elementary. Okay, and this is what it looks like. We have a very standard inductive, well, not non-inductive, but index family where we have is 0, and we know that a natural number is 0 if it's the Z constructor, and we know it's non-zero if we have the successor. And we know that if you have a natural number, it cannot be 0 and non-zero at the same time. It's impossible. Okay, straightforward, hopefully. Right, and this is quite nice, but we need to do a bit more. We need to sort of have our decision procedure to say categorically, is the number 0 or non-zero? And it turns out, and I'm looking at this to make sure I press the right button, that it's quite simple here, okay? And what we're saying is that if the number is 0, we return the constructor IZ, and if it's non-zero, we return the constructor left. So notice how this is positive in both the error case and the positive case, right? Which means I've got now more informative messaging or reports of why something failed, okay? Not that, and in this case, it's quite simple, and that it's either is 0 or non-zero, but if we scale up to more complicated things, we get more information to report, right? But I've only done is 0. What about non-zero? And it turns out we can reuse our definitions. We're programming. And I have a very simple function here called mirror, which takes an instance of decidable and swaps what's positive and negative around and does the same with the proof. Very naively, it does this. And the thing is, that's red because, right button, this might not what we want to do. Okay? And I'll explain that in a little bit. But this is quite cool in that I can just use this mirror from the either library just to swap what happens with a 0 and report it back. So I'm having a bit of code reuse here in a very positive way. I think that's quite nice. So let's revisit the working example. So here I've rewritten test and print in my framework. Not much has actually changed. So before, right button, so we have yes and no, but now we have left and right. But the nice thing in the error case is I've got something from the left-hand side and I'm using it at runtime. I'm printing out why this failed, which is quite nice. And so what does that look like? Well, if I press the right button, then this is what my REPL gives me, okay? So in the positive case, we have it as before, except it's right. We have all IZ, the easy case, right? But in the negative case, I now have a proof of any that, because the opposite of all is any, that everything is fine until we get to this point here where it's not fine. And not only do I have where in the list the error occurred, but why there's an error. And if you're doing anything with typing context or stateful typing context, we can now say why you can't work with something, which is really simple. And it all goes back to this idea of two rights lead to nothing. And if you use those two right things, it gives you more information. And to show you a bit more about what we had before, it's an improvement, I think. And I think that's quite cool and useful. So let's see, right. I want to talk about decidable equality because I think that's quite important. And because if you're doing any sort of proving or engineering, you want to say, are two things equal? Now, in Idris 2, we use an interface for this, but I've got two. Right, I hate this, right? So it's failure. Oh, you got to laugh at it, don't you? Right, so what we have here is our decidably equal. And what I'm saying is, we've got a function that holds something that I say is decidable in this framework, but that's not enough, okay? What we have to do, we have to provide evidence that our positive thing on the equal side goes to Idris's built-in equality to maintain that invariant that if you say it's equal, it actually does mean equality. And we do the same with the negative case that you can get void. Right? And then we can sort of say, well, can you provide me something that is decidably equal? And if you want REFL again, then you need to provide how you can get REFL from an explicit type. So just getting back to what we had before, and as you saw ahead, we can actually build a slightly better decidable equality where, given two things, we actually just say, look, if we know there's something that's decidably equal, then we can return the negative proof of y is equal, but then the reflective thing as well, and we do it generically with our interface. And I think that's actually quite nice. And it's quite useful and informative, right? It's all about, I want to tell users why something didn't happen just as much as why it did happen. Okay, so moving on, what have I done? Well, I've been slowly embracing this negativity in a while, and I've sort of gone through simple thought things to more extensive thought things. So looking at bottom, like I've been playing around with primitives, natural numbers, strings, where you need a lot of believe me's. So can we build up predicates that work on these things? And then go into more higher order things like pairs, lists, and trees, because I want to write programs or really elaborate. I want to build wealth. I like intrinsically typed terms. And so can I use these lists and things to build a positive view on elaboration? Okay, type equality of term, type equality, okay? And that's where I've moved on to, from very simple things to more complex things, looking at efficient de Bruijn indices like Guillaume has mentioned and Venn, and looking at big decisions going more of saying, look, I would do something more interesting, and I'm still working on a lot of this, okay? Going forward, do we have a recipe for it? And as you may have seen in that, we have 4 steps, which is I want to identify what's true and what's false. It's to go down the happy path is quite easy, but to talk about failure is quite hard. You have to refute a lot more evidence than you do have when it's positive, because it's easy to do the happy path, harder to do the negative one. Then you want to build your proof of void, do the 2 things you've done cancel out. And if they don't, go back to the start, go on and go on. But we also have to validate it. Okay, and the reason why we have to validate it is because the mirroring. So I've got a very simple higher order predicate that says, does something hold or does it not hold? Okay, very simple. But the key thing to notice here, I'm saying this is positive, this is negative. If I mirror this, then what happens here is the holds goes to holds, P holds not. I swap the 2 around, but I'm talking negatively in the positive case. And I don't like that, because if I'm mirroring something that the holds not is the positive, I want to say it's a positive failure and not a negative failure. And that's something I need to put my head around. But if I call mirror on the P on the itself, I'm swapping the polarity to get the right result, but the mirroring should work on the entire predicate. And if you build up more higher order predicates like any and all, you need to be aware of this. Okay, and this is something I'm struggling with at the moment, just like this remote, which is going well. But then another thing, think about, well, what if I do a more generic definition? If I want to reuse code in my library, and then, well, I could do something a bit more elaborate here. I can then do the swapping by hand, where I have what's positive and negative and just swap it around, which is fine. But then I'm doing it by hand. Is there a way to do this automatically? And the thing is, there might be other ways to do it, and I just don't know how to do it, right? I need to talk to people who like constructive negation, say, what are the semantics I can use to do this, and what are the design patterns I'm working with? So I'm about to be kicked out, but the one thing I want to talk about is informative error messages, okay? So in any first-year programming course, you say nothing fixes the billion-dollar mistake, and Decidable, I think, improves upon that, which is quite nice. But if you want more informative errors, then you think about either. Either provides you more information when you fail, okay? So if you want to backport this to existing structures, then I've got what is a commutative diagram and saying, well, let's add an error component to deck. You just fill with any messages you want to fill it with, and then you can use that to build something a bit more elaborate. And that's what I've been doing from the very beginning. And when I talked to Bob about this, he said, oh, you can do a bit more principle, which is where this whole constructive negation thing came in. And this approach of backporting gives you fantastic error messages. I've used it in my research over the last couple of years. And just a bit of a highlight is, this is what the all would look like. You have a predicate that takes gives you the error message, but you can recover decidability in a less informative way. And to finish, programs fail. We need to take into account that failure and report that failure to the user. And if we do it with void, we can't do that. If you do it with this approach, you can actually start telling the user why things failed, which is quite important. It's quite hard. I don't know what I'm doing. I need help with it. Okay. Thank you.